All right, in this video, we're going to look at limits of rational functions. So we're going to study limits of the form limits of f of x over g of x as x approach a. Now, so this is going to be the case where both f of x and g of x are polynomials. Okay, so you're going to recall that if both f and g are polynomials, then f over g is called a rational function, just like a rational number is a fraction of two integers. A rational expression is a fraction of two polynomials. Right. Note, however, that the ideas we are going to develop here, even though they're going to be developed under the context of rational functions, these can be extended to other quotient functions where the numerator and denominator are not necessarily polynomials both. Okay, so we'll demonstrate that as we work through some examples. Right, so there are going to be three cases that arise in the limits of the form. Let me call this equation number 1. So the first case is the case where f of a is not 0, or rather g of a. So if g of a is not equal to 0, then the limit can be obtained via direct substitution. So the limit is simply going to be f of a divided by g of a. So that is like the simplest case, if you like. Case 2, if this time g of a is equal to 0, but f of a is not 0, then this time what it means is that there is a vertical asymptote, asymptote at x equal to a, at x equal to a. So what that means is that if you plot a graph of y equal f over g, then at x equals to a, there is going to be a vertical asymptote. Now, whenever there is a vertical asymptote, the graph should not cross the vertical asymptote. And in fact, then there are going to be 4 cases that arise. I'm just going to quickly sketch through them. So if this is x equals to a, case 1, then the graph should not cross this vertical asymptote. So either on the left-hand side it goes to infinity, on the right-hand side it goes to minus infinity. This is one possibility. Another possibility is that both on the left-hand side and on the right-hand side the graph goes up to infinity. Remember, it is not allowed to do something like that. So like we said, the graph cannot cross the vertical asymptote. Okay, so this is the second possibility. The other two possibilities are the mirror reflections, if you like, of what we have just seen. So in case number 3, you could have the left-hand side going down to infinity and the right-hand side going up to infinity. In case number 4, they could both go down to infinity. So the graph, the left is going down to infinity, and on the right it's also going down to infinity. So these are the 4 possible cases if x is a vertical asymptote. So in terms of the limit, so to find the limit, we need to examine the left and the right hand limits. Okay, so to determine the limit, we examine the left hand limit and the right hand limit. As you can see from these cases, there are, well, 2 possibilities. Okay, either we have a case like this one, in which case the limit is going to be non-existent, because from one end the limit is going to be infinity, while from the other end it's going to be negative infinity. And remember, we said if the left and the right hand limits don't match, then the limit does not exist. The same situation happens if we've got something like this. This one is minus infinity. This one, excuse me, is positive infinity. And then in these 2 cases here, the limit is going to be plus infinity, and the limit is going to be minus infinity. All right, then case number 3 is the case where both f of a and g of a are equal to 0. Then direct substitution gives the following. So the limit f of x over g of x is going to be equal to f of a over g of a, which is going to be equal to 0 over 0. The the quantity 0 over 0 is called the indeterminate form. Indeterminate form. Indeterminate means that its value can not be immediately specified or found. More analysis is needed to determine what its value is. So this is called the indeterminate form. Now, thinking back to our theory of of polynomials, okay. So recall that if f of a is equal to 0 and f is a polynomial, what this means is that x equal to a is a root by the remainder theorem. Okay, so x equals to a is a root of the polynomial f of x, and x minus a is a factor. Okay, so the same thing of course applies with g, because g of a is equal to 0 as well. So that means what this situation implies is that f of x has got a factor x minus a. G of x also has got a factor of x minus a. So that means between the two of them there is a common factor of x minus a. So thus there is a common factor of x minus a between f of x and g of x. So to evaluate the limit, so to find the limit, we do two things. First, we factor out and cancel the common factor of x minus a. Then once we've cancelled out the common factor, then we can do direct substitution. Okay, then after that we do direct substitution. So that's how we evaluate that type of limit. All right, so let's have a look at some examples then. All right, so suppose we have these examples here. So in each case, the first thing we're going to always try is direct substitution. Then, depending on what happens with direct substitution, then it's going to tell us whether we are in case 1, case 2, or case 3. Sorry, this is minus 2 here. Okay, so substituting here, we're going to have 2 squared plus 2 over 2 squared minus 2. 2 squared plus 2 is 6. 2 squared minus 2 is 2. So this is 3, so that is going to be our limit. Okay. Then in part B, we have got 2x minus x squared all over x squared minus 4. If we substitute, it's going to be 2 times 2 minus 2 squared over 2 squared minus 4. 2 times 2 is 4. 2 squared is 4, so the numerator is 0. So is the denominator. So that tells us that we are in case 3. So there is a common factor of x minus a. A is 2. So we need to factorize. In this case, the expressions are not difficult, so we can factorize this. Quadratic expressions. X is common there. And this one is a difference of 2 squares. Okay. Now, these two terms here, one is the negative of the other. So what we might want to do is to factor out a negative here, and then we can write the numerator like that. All right, then x minus 2 is a common factor. Now, however, we don't divide by a 0 quantity. So, but in this case, since we're doing the limit as x approach 2, that means if x is approaching 2, x is not equal to 2. If x is not equal to 2, this is non-zero. So this we can cancel out because x is not equal to 2. Okay. So then this thing is going to be equal to the limit as x goes to 2 of negative x over x plus 2. Then after cancelling out the common factor, we can now do direct substitution. So this thing is going to give us minus 1 over 2. Okay. Then going to C, we have got the limit as x goes to minus half of 4x squared minus 1 over 8x cubed plus 1. Again, if we do direct substitution here, it's going to be 4 times negative 1/2 squared. Denominator is going to be 8 times negative 1/2 cubed. The numerator is going to be 1 minus 1. Denominator is going to be minus 1 plus 1. So again, this is case 3. So we have got a common factor is going to be a common factor of x plus 1/2. So if we factorize that, then and cancel out, and then this should be okay. For the numerator, it's quadratic, so we can, it's actually a difference of 2 squares. Straight away, we can write it like that. But for the denominator, it's a cubic. So what we're going to do is we're going to appeal to the remainder theorem and synthetic division. So according to that, if we do 8x cubed plus 1 over 2x plus 1, we must get a quotient here plus a remainder of 0. So we need to find this quotient here, and so that's where we're going to use the synthetic division. So if you bring minus half here, coefficient of x cubed is 8, coefficient of x squared is 0, coefficient of x is 0, and the constant term is 1. So if we drop down 8 here, so that's going to be minus 4 there, 2 here, and minus 1 there. So what this thing is telling us is that 8x cubed plus 1 can be written as 2x plus 1 into 8x squared minus 4x plus 2. So our limit we can write as follows. So we can write this as the limit as x goes to minus half of 2x plus 1 into 2x minus 1, all divided by 2x plus 1 into 8x squared minus 4x plus 2. And then, of course, since x is not equal to negative half, so we can cancel this out, and then this thing we can write as the limit as x goes to minus half of 2x minus 1 over 8x squared minus 4x plus 2. Substituting here, when I have 2 times minus 1 half minus 1, all divided by x, 8 times minus a half squared minus 4 times minus a half plus 2. The numerator is going to work out 2 minus 2. Denominator is going to be 2 plus 2 plus 2. So this is going to be negative 1/3 is our limit. Right, let's go to part D now. Alright, in example D, we have got the limit as x goes to 2 of 2x plus 1 divided by x squared minus 4. Plugging in 2 as usual gives us 2 times 2 plus 1 all over 2 squared minus 4. The numerator is 5, the denominator is 0. So straight away this is telling us that x equals to 2 is a vertical asymptote. Okay, so we're in case 2, so we need to examine the left hand limit and the right hand limits. We're going to do this using 2 approaches. The first one is the numerical approach. Which we have already seen in the video under introduction of limits. So all we do really is we do a quick numerical analysis of the situation on the left hand side of x equals to 2 and on the right hand side of x equal to 2. So if we start with the left hand side here, So we're like immediately just slightly to the left hand side of 2. So somewhere here, and then getting closer and closer to 2. So we're going to have x and y. So if we start with 1.9, remember this is our f of x. So we're going to bring in the calculator here. So we're doing 2x plus 1. So it's going to be 2 times 1.9 plus 1, then all divided by open brackets. So it's x squared minus 4, 1.9 squared. So 1.9 squared minus 4. Okay, so that gives us minus 12.3. Then we're going to go to 1.99. Let's say 3 9s. So I'm just going to add 2 9s here. 9, 9, and then 9 and 9 here. Okay, that gives us negative 1249. So negative 1249. That is good enough, and it shows us that as this is getting closer and closer to 2, this one is going to negative infinity. Okay, so we can say therefore the left hand limit is negative infinity. Then we're going to do the same analysis on the right hand side of 2. So this time we're starting somewhere here, and then we're just getting close to 2. So if we start with 2.1, go back to the calculator. So this time we're just going to replace this with 2.1, replace that with 2.1, and the value is 12.7. Then we're going to do 2.001. And so just change this to 001, 001. And we can see now it's 1250. So this time, as this goes to 2, this is going to positive infinity. So right hand side limit is positive infinity. What it does mean is that a crude representation of the graph around x equals to 2 is going to do something like this. So here it goes down to negative infinity, and from this side it goes up to plus infinity. So since the two limits do not match, that means the limit of 2x plus 1 over x squared minus 4 as x goes to 2 does not exist. Because remember, for the limit to exist, the two need to exist and they need to be equal. All right, method 2 now. In method 2, we just do a an analysis of the signs, okay, of the function. So what we're going to do is we're going to start again on the left hand side. On the left hand side of x equals to 2. So we're going to say if x is slightly smaller than 2, okay, than 2, then we're going to analyze the sign of the numerator and the sign of the denominator. If x is slightly smaller than 2, they were just interested in the sign. This thing, if x is slightly smaller than 2, this thing is still going to be positive plus a positive number. So the numerator is going to be positive. And then in the denominator, if x is 2, this minus this is 0. If x is slightly smaller than 2, then this is going to be smaller than 4. So this minus this is going to be negative. So that means the quotient is going to be negative. And then from there, we can conclude that the left-hand limit is going to be negative infinity. It's all about the sign of the quotient slightly to the left of 2. Then on the right hand side, if x is slightly bigger than 2, then this time the numerator is still going to be positive. The denominator, though, is now going to be negative because this is now bigger. Denominator is now going to be positive. I mean, this is now bigger than, it's going to be bigger than 4. So that's going to be positive as well. So that tells us that the right-hand limit is going to be positive infinity. And therefore, we can now conclude exactly the same way as we did in the first method. In E, we've got the limit as x goes to -1 of 2x minus 1 all over x plus 1 all squared. If we substitute, we are going to get -3 over 0. So again, this is telling us that x equal to -1 is a vertical asymptote. Okay, so we need to do the left hand and the right hand limits. So on the left hand side of x equals to -1, so now be careful here, this is 0, this is -1. The left hand side, you've got so if we are somewhere here and we are going towards there, so we're going to have -1.1, for instance. Okay, then -1.001. Okay, this time we are substituting into this function here. So we're going to have it's 2x minus 1 of, so 2 times -1.1, then -1 here, Then in the denominator, we have negative 1.1 plus 1 plus 1, negative 1.1 plus 1, and then this is all squared. Okay, so that's giving us 320. Okay, so come back here. Negative 320 it is. Then I'm going to change this to negative 1.001. We're getting closer and closer to negative 1 from the left. And you can see this is negative 3 million something. Okay, so we can see that as this is going to negative 1, this is going to negative infinity. Then we're going to do something, the same thing on the right hand side of negative 1 this time. So this time we're going to have the likes of 0.9, negative 0.9. So go back to this calculation. All we're going to do is to replace this by 0.9 and that one by 0.9. Okay, that gives us negative 280. Then if we do 0.999, so that's going to be negative 2 million something. So again, as this is going to negative 1, this is going to negative infinity. So this time, the left-hand limit is negative infinity. The right-hand limit is also negative infinity. Graphically, what it does mean is that this function around x equals to negative 1, okay, is going to go to it's negative infinity. It's going to go to negative infinity this side. Is also going to go to negative infinity that side. Okay, so we conclude the limit as x goes to negative 1 is negative infinity. All right, one more to do. In example F, we have got the limit as x goes to 0 of 2 minus square root of x plus 4 divided by x. If we substitute, this is going to give us square root 4 is 2, so this is 0 over 0. Now notice that here the numerator is not a polynomial because of the square root, but we are going to use the same ideas. What this is suggesting is that there is a common factor of x in the denominator that is pretty obvious. In the numerator, it looks like that common factor of x is somewhat obscured by the square root. So one of the methods to apply here is to remove the square root in the numerator. Removing the square root is actually called rationalizing the numerator. So we are going to rationalizing means making it a polynomial, so it means removing the square root. That we're going to do by multiplying the numerator by something or a term that is going to make the numerator into a difference of two squares. So that we are going to achieve if we multiply the numerator by a term like this with an opposite sign there. So we're going to multiply the numerator by that. But if we multiply the numerator by that, we need to also multiply the denominator by the same term. Otherwise, we have altered this expression here, which we don't want to do. Then, of course, then the numerator is now a difference of two squares. And we know what that means is that this is going to be the first term squared minus the second term squared. In the denominator, we're just going to have these two terms. We don't need to multiply anything out really. Then the square root squared is actually going to undo both of them. So the square root and the square undo each other. So this is going to be 4 minus the brackets are important here. Right, and then if we remove the brackets in the numerator, since now the square root has been removed, so the numerator now, as you can see, is a polynomial. So that was the whole point of that rationalizing exercise. So that polynomial now simplifies to just negative x. And as we had theorized that there is a common factor of x, well, there is the common factor. So at this point, we can now cancel out the common factor of x. And as we said in the notes, once we have cancelled out the common factor, then we can do direct substitution. So after this, it's going to be negative 1 all over 2 plus square root 4. So this is going to be negative 1 over 4, excuse me, and that is going to be our expression. So that's method 1. There is a method 2 here, which we can use, and this one uses the binomial theorem or the binomial series. So what we do is we apply the binomial expansion to this term. Now, since x is going to 0 in this calculation, so we're doing the limit as x approaches 0. That means between these two terms here, this one is the smaller. And if you're going to recall from our study of the binomial expansion, for powers that are not positive integers, we always need to start with the bigger term. So we're going to write this thing like that. Then for purposes of this, we only need the first 3 terms. Then that's going to be good enough. So the first term is going to be 4 to the power 1/2. Second term is 1/2 times 4 to the power -1/2, and then times x. The third term, which is the last term we need, will be 1/2 times -1/2 over 2, 4 to the power -3/2. Just make sure that you can remember how to go through these. Then the first one is just 2. The second one, x to the 4 to the power -1/2 is just 1 over 4 to the half, which is 1 over 2. So that's going to be x over 4. And then this one is going to simplify to x squared over 64. And then there is going to be lots of other terms. Now, the thing to keep in mind here is that the powers of x are going up. So the next term is going to have x cubed, x to the power 4, etc. Now, so if we take this and substitute it into our limit, so this is going to be 2 minus square root of x plus 4 all over x. Now, the second term, we are going to substitute this binomial expansion over 64. Then we're going to remove the square brackets. So remember, when you remove the square brackets, the signs inside the square bracket are going to reverse. And then these two terms are going to cancel out. So we're going to have limit as x goes to 0 of negative x over 4 plus x squared over 64, etc., etc. And then all these terms here, remember we said this is x squared, so it's going to have x cubed. All the terms here are going to be multiples of x. So there is going to be a common factor of x that we can factorize. So that's going to be x over 64, etc. There is the common factor of x now, which we've managed to extract using the binomial theorem. So we cancel out. After cancelling out, then we can do direct substitution. So is now going to be negative 1 over 4 plus x over 64, etc. So if we plug in x equals to 0, then all these terms are going to vanish because they're all going to involve 0. And so you can see we now have the same solution that we obtained earlier. All right. We are going to give you just a few examples to try out. And then, yeah, so just a few examples. All right, so if you want to take a few minutes, have a go at these 4. Pause the video, and then when you press play, then you can compare with our answers, which will follow shortly. All right, so we now scroll down to our solutions. For G, if we plug in x is 1, this just gives us 6/3, so the limit is 2, so that's case 1. For H, if we plug in -2, we get the indeterminate form 0/0. So that means there's a common factor of x plus 2 in both the numerator and denominator. So using synthetic division, we find the quotient for both of them. This is the numerator, 2, 3, -2, 2, 3, -2. This one is the denominator, 3, 8, 4. So that means we can factorize the numerator and the denominator like this. Of course, since these are quadratic, we could obtain these using the methods, the standard methods of factorizing quadratics. And then cancelling out the common factor and then plugging in -2 gives us 5/4. In the next one, if we plug in x is 1, we get 0/0. So again, this time it means x minus 1 is a common factor. This time you can't factorize this using theory of quadratics because these are not quadratics, so we just use our synthetic division and remainder theorem, and these are the two factors here, and then we cancel out the common factor and plug in x is 1 and find that the limit is actually equal to 2. And then for the next one, we have got a square root, so we need to rationalize the denominator this time. So we follow the same procedure, and so once the square root has been removed, we notice that there is that common factor of x. And then once we have factored out and cancelled out the common factor, then we can plug in x equals to 0, and that gives us the limit to be -5. All right, so thank you very much for watching. Hopefully this has been useful. Please do subscribe so that you can get notified whenever we post new stuff.